scenarios with separated parties who have inputs and outputs, and they get certain correlations. And we talked a bit about the general problem of being given some set of correlations, finding out whether they're local or non-local, and also whether they can be obtained from measuring a quantum state or not. And we saw that one ends up with these different sets. So the local correlations form polytope, which we're calling L. And the facets of that polytope are the L inequalities. So if you want to check if your correlations are local or not, it reduces to the problem of checking whether a vector lies within this polytope. And that's a linear programming problem. Essentially, you just need to, given the vertices, figure out all the facets, the L inequalities, and check it against those. There's also the set of all non-signaling correlations, and that's this bigger polytope P. And then in between those things is the set of correlations you can get from measuring quantum states, which is Q. And we saw that these containments are each strict, because there are non-local quantum correlations, and there are also correlations that are more non-local than quantum. And now in this sort of discussion at the end, we had an interesting bit of chat about the problem of determining whether some correlations are quantum or not. And some of that I was sort of talking from memory as best I could, so one or two of my answers were, let's say, vague. So I'd like just to say one or two things about that before carrying on. So first of all, there is this interesting work, which I've, given more lectures I would have gone through in detail, but I'm not going to, by Vasquez, Peronio, and Asin, who defined a sort of hierarchy of sets. So here's our quantum set Q, which is convex, but not a polytope. And the hierarchy of sets looks like this. There's this bigger one, Q1, and here, Q2, and so on. What I said was that these things converge on the quantum set. That wasn't precisely right, because there is a little subtlety there, which I just feel I ought to mention. Where's the bit about quantum things? So there we are. I said correlations are quantum if they can be written in this form. So that's how I'm defining my set Q. Now, there's a slightly different definition you can give where you don't write these Alice's and Bob's measurements as having a tensor product form like this. But all you demand is that all of Alice's measurements commute with all of Bob's, rather than assuming they have this tensor product structure. Now, in finite dimensions, that makes no difference, that's known. But in infinite dimensions, it's unknown whether it makes a difference. So, we can define a set called Q prime, which is defined similarly, but only demanding that the Alice measurements commute with Bob's measurements. And it's actually to Q prime that these things converge. So I just felt I owed you the sort of precise statement of the thing there. We also talked a little bit about the sort of complexity issues here. So the way these Qs are defined, it's a beautiful thing actually, but also a fiddle to write it all down, so I'm not going to do it. But it sort of works like this. Q I, for example, is defined like this. You end up writing down a matrix, and some of the entries of that matrix are the probabilities that define the set of correlations, and other entries are left blank. And the problem is, can you fill in the rest of those blank entries in such a way that the matrix as a whole is positive semi-definite? If you can, then your correlations belong to the set Qi. And that is a semi-definite programming problem. The tricky thing is that the size of that matrix increases exponentially with I as we go down here. Now, of course, one other remark this Q, as I've defined it, doesn't make any assumptions about the dimension of the quantum state that's shared between Alice and Bob. We could define some other states, some other sets. You could say, suppose Alice and Bob have a qubit each, and they're measuring qubits, what correlations can they get now? Well, we could write, let's define that set. We could write it as, I don't know, Q. I'll put 2 times 2 up here to indicate these are 2-dimensional systems that are being shared, and that'll be some subset of the big Q, of course. You'll notice that I haven't even drawn this one as a convex set, because it's not convex. But it will be contained in another bigger one, which is Q 3 times 3, the correlations you can get by measuring Q-trits, and so on. And these ones will approach this Q here. So putting all this together, we do have some kind of algorithm that would tell us whether some given set of correlations is in, well, at least in this Q. Yeah, okay, apart from that. So determining whether some correlations are in this one or not, that's a solvable problem because it's just qubit states and measurements on qubits. So there's a bounded set of all qubit states that you have to consider. So a brute force numerical search would work if nothing else. What we don't know is a way of determining whether the correlations are in there that scales efficiently with the dimension of the quantum systems that you're sharing. So the problem gets harder and harder as this set gets bigger. And then coming from the outside, we can solve these semi-definite programming problems. And unfortunately, of course, they get harder and harder as well. Okay, so that's, I think that's pretty much all I wanted to say about that. Just to give it a slightly better response to the discussion that we were having. So let's move on. I've got a little bit more to say about non-locality, and then we're moving on to a new topic, which is contextuality. So I want to talk a little bit about generalizing the Bell scenario. The first and most obvious way in which the scenario I've described can be generalized is to allow more parties. So here we've got 3 instead of 2, inputs X, Y, Z, outputs A, B, C. I'm not going to say much about this. The basic formalism is similar. You get a local polytope, a non-signaling polytope, a quantum set. You still get this idea of this hierarchy. So with respect to that sort of basic formalism, not much changes. You can visit all over again the problem of looking for information theoretic principles that would characterize the quantum set, and people have done that. There's one called local generality, for example, which I'm not going to talk about. But what I'd like to do is talk about some much more recent work that generalizes the Bell scenario in a different way. So let me introduce this thing. This is a causal network. A causal network is a directed acyclic graph with random variables on the nodes of that graph. And the idea is that the arrows indicate causal relationships between these variables. So here, for example, we see that V is not a cause of W because there's no arrow from V to W. But V and W can be correlated with one another because they have a common cause U. Similarly, X can depend on U here because indirectly U is a cause of X. But it's not a direct cause of X because there's no arrow straight from U to X. The only way X can depend on U is indirectly with V. So precisely what that means, those remarks, is that they impose constraints on the joint probability distribution over all these variables. And we say that a joint distribution is compatible with that graph. Well, in this example, if the following holds, so there's a joint distribution over U, V, W, X, Y. You can always, of course, write it in this form, X given the others, and Y given those, and so on. And to be compatible with the graph, we're saying that x, the probability of x conditioned on all the other nodes, is equal to the probability of x conditioned on v, because v screens off x from the others. P of y given VWU is similarly just P of y given v, because v screens off y from the others, and so on. The general rule is like this. So we're given a graph of nodes x1 to xn. The joint distribution P over x1 to xn is compatible if for each node the probability of xi conditioned on its parents and also its non-descendants in the graph is equal to the P of xi conditioned only on its parents. So the parents are just the nodes that have an arrow going into xi. The non-descendants are nodes which are not a descendant of x, and the descendants of x are the nodes for which there's some path from x to the node. Alright, so those things are causal networks. Now we can start to think about the Bell scenario in these terms. It corresponds to the graph above. We're going to treat the measurement settings now as random variables themselves. So x and y are the measurement settings. Now we didn't really talk about this much before, but when establishing non-locality, it's crucial that measurement settings are independent of putative hidden variable lambda. So there's that sort of famous loophole in Bell's theorems that you can get around it if you allow correlations between, let's say, Alice's setting and the hidden variable lambda. But most people take that to be a very implausible idea because it's difficult to reconcile with, let's say, Alice's free will. Anyway, this independence is encoded by the above graph because there's no arrow from lambda to x or x to lambda, and they have no common cause. So any joint distribution compatible with this, that must be independent. And the locality condition is also encoded by that graph. For example, given x and lambda, A must be independent of B and Y. Because conditioned on its parents, these non-descendants here must be independent of A. So that's the locality condition. So one might ask, which joint distributions over A, B and X and Y can arise as the marginal of some distribution P over A, B, X, Y, lambda, which is where that joint thing must be compatible with this graph. Maybe I should say, lambda here I'm not taking to have a sort of a fixed dimension. So I'm just asking which joint distributions can arise as the marginal of some distribution for some variable lambda, which can have any dimension, any number of values. And in fact, we've answered this question already, because we characterized the local distributions. So the answer is it's those joint distributions such that you can write the joint as P of x times P of y times P of AB given xy, where this conditional P of AB given xy is a set of local correlations, meaning that the corresponding vector is on the local polytope. So that one we have answered. But now you can start to generalize this in all kinds of ways, you see, and here's a sort of pretty example which has appeared in a few times in the literature now. Here's a different graph. Now we've got three nodes which we can think of as source nodes or unobserved nodes. One has lambda on it, one has mu, and one has nu. So think of those as hidden variables if you want. And there are three observed nodes where the variables are measurement outcomes. Those are A, B, and C. And note that in this case there's nothing corresponding to a measurement choice. All Alice is doing here is producing an outcome A. There's nothing like a choice of measurement for her. Same if we have a Bob here and a Charles there. And in this case we'll say that a joint distribution over A, B, and C is classical if it can arise as the marginal of a joint distribution over all the variables that is compatible with that graph there. Which to be compatible with that graph there, it must be that the joint distribution satisfies this thing. So in particular, the key aspect here is that the lambda, the mu, and the nu must be independent from one another. That's the constraint that makes it this non-trivial. So, for example, we could consider these correlations. Here A, B, and C are perfectly correlated. Either they're all 0 or they're all 1, probability and half each. We could ask, is this classical? And the answer is no. No way you can get that from this kind of setup. There's a rough argument that makes it quite easy to see. If you just look at this, you have to have that A is always equal to B. Either they're both 0 or they're both 1. The only way you can have A always equal to B is if A is actually independent of mu. The reason for that is that mu is not shared with B. B doesn't know what mu is. But if A is independent of mu, then there's no way for A to be correlated with C, because mu is the only thing they share. So that's the hand-wavy argument. If you want to do a more precise thing, one can prove this theorem, which is what Tobias Fritz does in this paper. The theorem says that any classical distribution over ABC satisfies this entropic inequality. So mutual information between A and B plus that between A and C is less than or equal to entropy of A. Here's a quick proof of that thing. It just uses standard properties of entropies and mutual informations. Mutual information between A and B, that between A and C is less than or equal to that between A and lambda, and between A and mu. That we can expand out just using the definition of mutual information. The submodularity of the Shannon entropy, that holds. Hence, plugging that in, we get this inequality, and we get this one. However, since lambda and mu must be independent from the graph, that term is 0, and that gives this result. Okay, so there are some joint distributions, at least, that classically you cannot get from that thing. In the quantum case, we might consider that those unobserved hidden variables are replaced with quantum sources. So here we have a source of a pair of quantum particles, which might be in a joint state rho. Here they're in a joint state sigma, and here in a joint state tau. And again, we impose that the sources are independent, so the joint state of those three pairs of particles must just be the product of rho, sigma, and tau. And what can happen here, when an observer, Alice, can perform some joint measurement on the two quantum particles she receives before outputting the classical variable A, similarly Bob and Charles, and then a distribution is quantum if there exists states and measurements that produce E of A, B, C. So essentially that means you can write it in this form, where these indices refer to the 6 different quantum particles that are being produced. So you might ask, what is the set of quantum correlations that you can get on this thing? And you get some quantumly that you couldn't get classically. Well, here's a start. The theorem says that actually any quantum distribution also satisfies this. That's the same inequality we had for the classical case. That's in this very recent paper here, Johansson, Raylal, Pusey. So that tells us straight away that even with quantum sources you can't get those perfect three-way correlations, because those things violate this inequality if you just plug them in. So we might ask then, does there exist at all a quantum distribution which is not a classical distribution? Or we could even generalize further and say, well, what if these sources are actually making those PR boxes we talked about last time? could you obtain a distribution that way, which is not a quantum distribution? Well, if we allow these variables a, b, c to be 4-valued, then the answer is yes to both questions, actually. For details, see that paper I mentioned by Tobias Fritz. I won't go through the argument. On the other hand, if we restrict a, b, c to be binary, then as far as I know, no one knows. So even in this very sort of simple case, we don't know if there are quantum correlations that go outside the classical set. Yes?
So in that binary question, if you ask the transitive closure of the two questions, does there exist a PR box that's not, or distributional tape on PR boxes that's not classical, then they're both polytones, so they should be able to deciding the question, right?
No, so I should have, maybe I should have said some words about this. So here, we don't have that simple polytope picture. Actually, even characterizing the set of classical distributions that you can get seems to be a much more complicated problem. And in fact, it's not even a convex set,
Because
like
the
the
condition
polytope.
of sigma and rho being independent, it's not a linear condition.
Exactly.
Okay, I withdraw my
Yeah.
question. But thanks for answering.
So characterizing completely the set of classical correlations you can get on this thing seems to be, a difficult problem, and one that so far we don't know much about.
John, so this fact that the statistics aren't convex anymore comes from what exactly? In fact, you've got more than one source.
Yes, it's because we have these three sources and we're demanding that they're independent. So if you think of one set of joint probabilities P of A, B, C that you can get using some underlying hidden variables, and now think of another set P prime of A, B, C, which you can also get classically. It's not obvious that you can just make a mixture of those two things and get that classically. Because you can't just sort of take the corresponding mixture of distributions on the underlying hidden variables, because now they wouldn't be independent anymore.
And huge body of work studying these things is based on properties of convex sets. So so that's fine as far as it goes, but maybe that work is quite limited and actually be able to address these much more general, perfectly valid scenarios.
Well, so anything based on convex sets is extremely limited. As soon as we go just beyond the simple sort of scenario.
Has that generally been realised for a long time? That's not a criticism I've really heard.
So it's only been relatively recently that quantum physicists have sort of latched onto these examples. I mean, as you might imagine, this generic problem of classical causal networks and what marginal distributions can you get on subsets of the nodes has been studied by computer scientists and things like that. So there are some results there, to do with characterizing classical sets. Very little to do with knowing much about the quantum set and when it's bigger or different or anything like that. Okay, and that pretty much brings us to the end of what I'm going to say about Bell and non-locality. It's a sort of summary. In Bell scenarios, the problem of classifying local versus non-local correlations is solved. It reduces to membership of a vector in a polytope. The problem of classifying quantum versus non-quantum is more difficult. For interesting progress, see this paper. That's one where this hierarchy is quite heavily talking about. And finally, in the more general scenarios, like we've just been seeing, classifying the sets of either classical or quantum correlations seems to be a difficult problem. Now, there's all kinds of stuff that I could have gone on to say if we had more time. There are many applications of quantum non-locality, so it's of use in solving communication complexity problems. It leads directly to something called device-independent quantum key distribution, where separated parties can send secret messages to one another. device independence means that Alice doesn't even need to trust what her quantum device is doing. She could have purchased it from the eavesdropper, let's say. And yet still, rather remarkably, they can get some kind of security there. And also a sort of related thing, device-independent randomness generation. All active research areas at the moment, but we won't have time. And something that's really, I don't suppose anyone has thought about too much yet is either the study of these generalized Bell scenarios lead to new applications. All of these are based on the sort of standard Bell scenarios that we started with. Alright, which brings us to part 2, which is about contextuality. So we're going to start with another one of the famous no-go theorems for quantum physics. The first was Bell's theorem. The second is the Cauchy-Specker theorem. So I'll go through the sort of traditional statement of this theorem first, and then start to say some other things. First of all, quantum observables, of course, correspond to the mission operators. And the expectation value of an observable corresponding to G is just given by trace of rho G for a state rho. Now we're going to suppose again that a quantum state is an incomplete description of a quantum system, that there are some underlying hidden variables. Previously we made an assumption like that, and then we showed that if the hidden variables obey Bell locality, then you cannot recover the predictions of quantum theory. Now we're going to forget about locality, but we suppose something else. Suppose instead that the hidden variables are deterministic, first of all, which means that they specify a definite value for each quantum observable, such that measuring the observable simply reveals that value. And suppose further that the outcome does not depend on the context of the measurement. In other words, it only depends on the mission operator being measured, and not on how the measurement was carried out, nor on what other observables are being measured at the same time. Well, hidden variables satisfying those assumptions are non-contextual. So if we just restrict to projection operators, for example, what that amounts to is this. Non-contextual hidden variables can be thought of as defining a map that takes each projection operator into either 0 or 1. Such that if P and Q project onto orthogonal subspaces, then lambda of P plus Q is lambda of P plus lambda of Q. And lambda of the identity is 1. Or equivalently again, non-contextual hidden variables would define what I'll call a KS colouring of the set of unit vectors in a complex Hilbert space. So let's assume finite dimensions. KS colouring is a map lambda that takes each unit vector to either 0 or 1, such that if a set V1 to Vd form an orthonormal basis, then the sum of those values is 1. In other words, exactly one of them gets the value 1 and the rest gets 0. And the non-contextual part of this is, of course, that the value you assign to a particular vector doesn't depend on which orthonormal basis you're considering that vector to be part of. And then the Cauchy-Specker theorem says that if the dimension of the Hilbert space is greater than or equal to 3, then the KS colouring of the unit vectors doesn't exist. So that was originally from 1967. Actually, I mean, that result was already noticed prior to that by Bell, who pointed it out as a consequence of Gleason's theorem. So sometimes it's called the Bell-Cauchy-Specker theorem. What Cauchy and Specker did was provide an explicit construction of a set of 117 vectors and proof that that set is KS uncolorable. So in fact, there is their diagram representing the set of 117 vectors, which they show is uncolorable. And a smaller set of 33 vectors was constructed by Asher Perez, also shown to be KS uncolorable. There's a picture of that set. Yeah, I think someone else did a set with 31 or something. Okay, so much for the Cauchy-Specker theorem. There is no non-contextual hidden variable interpretation of quantum theory, is what we should take away from that. But I'd like to tell you about a curious loophole in that argument, which was discovered by David Meyer. And he, following some work by some mathematicians, Gonzel and Zaks, he proved the following theorem. So let S be the set of unit vectors in R3, we're just thinking about R3 now, which have rational entries. Well then S in fact admits a KS colouring. And this despite the fact that when we were just doing KS proofs in 3D, well they were in 3D complex Hilbert spaces, you only needed 33 vectors to get a contradiction. Here we have a set of vectors which can be coloured in the appropriate way. And this set is dense in the set of all unit vectors in R3, meaning that for any unit vector in R3 I can find one with rational entries that's arbitrarily close to it. Furthermore, the set of orthogonal triads in S is dense in the set of orthogonal triads in R3. And here's the proof, which I'd like to go through just because it's rather cute, this thing. So each unit vector V with rational entries can be associated uniquely with a triple of integers, x, y, z, such that V is some constant times x, y, z, and also x, y, z have no common divisor. Now note that x squared plus y squared plus z squared is a square, a squared integer. And it follows from that that exactly one of x, y, and z must be odd. Now if V and V prime are orthogonal, then the corresponding triples, x, y, z and x prime, y prime, z prime, must differ in which entry is odd, since this equation holds from the orthogonality of V and V prime. And therefore a KS colouring is obtained quite easily. Just let lambda of V, the value that we give to a particular vector, be 1, if and only if it's the corresponding integer z that is odd. And if it's x or y that's odd, then this valuation gives 0 to V. And that way we're assured that for each orthogonal triple, exactly one of them gets the number 1. And we have a non-contextual value assignment. Now this was extended by Bob Clifton and Adrian Kent, who give colourings of dense subsets of complex Hilbert spaces in arbitrary finite dimensions. So it's not just a thing that works in 3 real dimensions, like we just did. Now this started quite a sort of argument in the literature. David Meyer titled his paper, it was something like finite precision measurement nullifies the Cauchy-Specker theorem, and people obviously found this provocative and wrote all sorts of argumentative papers. And I mean, of course, as a mathematical result, it's perfectly sound. The idea goes something like this, is that you could have a sort of underlying hidden variable model which makes a non-contextual value assignment only to the vectors within one of these dense subsets. And whenever you're actually doing a measurement on a system in a lab, in real life you can't, I mean you may be aiming to measure a certain orthogonal triad, but you can't sort of establish exactly the orthogonal triad that you're measuring. So there's always the possibility that your measurement is slightly different from what you were aiming for, and you've actually sort of coincided with triad or an orthonormal set of vectors from the colorable set. And so the idea is there could be a sort of theory that says that actually all possible measurements are those measurements from the colorable set, and then assigns non-contextual hidden variables to those. So I'm not going to say too much more about that. I'm just going to leave it with you to decide for yourself whether the Cauchy-Specker theorem has been nullified or not. It is a nice thing. What I'd like to do move on to a different topic, which is more operational notions of contextuality. So the standard Cauchy-Specker notion of contextuality that I've just been through is closely tied to the quantum formalism. It concerns colorings of the vectors in a complex Hilbert space. It also assumes deterministic hidden variables. Whereas Bell's theorem, by contrast, involves only empirically observable probabilities and puts a constraint on the kinds of models that could recover those probabilities. So you might ask, is there some more operational notion of contextuality that doesn't make explicit reference to the quantum formalism? And that's what I'm going to talk about now, following some ideas of Specker's. So consider this basic sort of setup. We'll be considering a quantum system of dimension d, let's say. This here is a preparation device. So it prepares the system. According to quantum theory, it will prepare it in some quantum state. Here's a little chap operating the device. Here's the system which comes out. Now we'll assume that the system has a hidden state, or I've switched over to using Rob Specken's terminology now, so I'm calling it an ontic state. And when you prepare the system using this particular device, the device prepares different values of lambda with different probabilities, so it corresponds to some distribution mu p over lambda. And then we perform a measurement on this system. So here's a measurement m with some, let's say, finite number of different outcomes. K is a possible outcome of the measurement. And this here, I'll call it a response function. This is the probability of getting outcome K when you did measurement m, and the ontic state was lambda. So what I'll call an ontic model for this system will define all of those things. Some space of ontic states lambda, for each preparation p, a distribution mu over lambda, for each measurement m, an outcome k, a response function, psi understood as the probability of getting outcome k when measurement m is performed, and the ontic state is lambda. And of course, we're going to require of an ontic model that it recovers quantum predictions. So that means that when we integrate over the lambdas, and we integrate over the probability distribution times the response function, we should recover the quantum probability for getting outcome k, which is given by this, where rho p here is the density operator that quantum theory associates with that preparation, and E is the positive operator that quantum theory associates with outcome K. Now we're not going to assume anymore that these ontic states are deterministic, because that's quite a restrictive thing to assume. So ontic states can just predict probabilities for different measurement outcomes. We'll say that an ontic state lambda is measurement non-contextual if this thing, this probability, only depends on the positive operator that quantum theory assigns to the outcome. So what that means in particular is that it doesn't depend on how you implemented the measurement, or it doesn't even depend on the full set of positive operators, that is the full measurement. It only depends on positive operator characterizing that one. So it follows that a measurement non-contextual ontic state defines a map that takes positive operators to probabilities. Some abuse of notation, you could write it like that. And finally, we'll say that an ontic model is measurement non-contextual if all the ontic states in that model are measurement non-contextual. And now we're going to introduce a sort of parallel notion, but for preparations rather than measurements. So, an ontic model is preparation non-contextual. This distribution over ontic states associated with the preparation method P only depends on the quantum state row that is produced by that preparation, and not on any other details about the method of doing this preparation. So, for example, the qubit state I over 2 could be prepared by either of the following methods. You might flip a coin and then prepare 0 on heads, 1 on tails. Or alternatively, here's a different method. You might flip a coin and prepare plus, meaning up x on heads and minus on tails. And forgetting about the outcome of the coin flip, either way you get I on 2. And this condition of preparation non-contextuality would demand that the resulting distribution mu over lambda is the same for both methods. And an ontic model is fully non-contextual if and only if it's both measurement and preparation non-contextual. So as a little aside, I think it's worth asking, why do we even care about this, or why is this some kind of natural constraint? At least in the case of Bell's theorem, we have the idea of locality, we have special relativity, so we understand why it might be natural to demand that things are local. But why, for example, does preparation non-contextuality matter? Well, a sort of rough argument goes something like this. If you think about Bell's theorem again, you can always write down a non-local hidden variable model which recovers the quantum predictions. However, one is faced with a new problem. Generically, a non-local model that you write down will lead to signaling even at the operational level. That's the thing that we don't have in quantum theory because of the no signaling principle. So to prevent this, to recover the fact that there's no signaling at the operational level, the model will need to be finely tuned. And then you have a sort of explanatory problem of explaining why, how that fine tuning comes about in the model. Well, a similar argument applies to either measurement or preparation contextual ontic models. If you had a model that's, let's say, preparation contextual, then there would be some difference in the model. For instance, the distribution on lambdas corresponding to some preparation P would be not equal to the distribution corresponding to some preparation P prime. And yet, it could be that P and P prime prepare the same quantum state, meaning there's no difference you can observe at the operational level between those two preparation methods, even though there is a difference at the underlying ontic level. And somehow the underlying model will have to be finely tuned to prevent there being any difference at the operational level. Okay. So that's why we might want these things. Finally, just to finish off this little string of definitions, a theory is contextual if some system in that theory does not admit a fully non-contextual ontic model. So a fairly easy theorem. First of all, there does exist a measurement non-contextual ontic model for a quantum system with any dimension. So without wanting to be too formal, here's the proof sketch. You simply let the ontic state be identical with a quantum pure state with the response function defined by the Born rule. And then immediately, probabilities given to measurement outcomes, of course, depend only on the positive operator. So that's easy. What about preparation contextuality? Well, first, to make any statement, we do need to impose something further. So we're going to impose this rather natural constraint. Consider a set of preparation procedures. Let's call them P1 up to PR. And suppose that an experimenter selects one of these at random, perhaps by rolling some dice. And let the probability of selecting procedure PI be QI. Well, viewed as a whole, this defines a new preparation procedure. Call it P. So P is the procedure of rolling some dice and then doing this or that or that. And we're going to impose that the distribution over lambdas you get by doing that is just the corresponding mixture of the distributions over lambda for each of the PI. The only way that could be violated would be if the lambdas somehow knew about sort of the outcomes of this coin toss that we're doing, but that might be a completely separate thing. And here's the theorem. Given that constraint, there does not exist a preparation non-contextual ontic model for any quantum system of d greater than or equal to 2. So it's nice that it even holds in d equals 2, because remember the usual Cauchy-Specker theorem only holds in dimensions 3 and greater. And here's a proof of that thing. So all of this stuff is pretty much from the same paper, which is by Speckens. We're going to consider a bunch of different preparations of the identity on a qubit. This is a plane in the Bloch sphere, so sigma little a and sigma big A are orthogonal pure states, so are big C and little c and big B and little b. So one way of preparing the identity is to toss a coin and then prepare either little a or big A, or I can toss a coin and prepare either little b or big B. Similarly with the C's, but another way is to take a mixture of a third each of the lowercase sigmas, sigma A, sigma B, sigma C. They mix to give the identity, or a third each of the big A, big B, big C. Now notice first of all that if two of these are orthogonal, for example little a and big A, that must mean the distributions on over lambda don't have any overlap. So mu little a of lambda times mu big A of lambda is 0. I'm writing a little roughshod here over some sort of measure theoretic niceties, so except on a set of measure 0, maybe I should say, or something like that. Okay, similarly, mu little b, mu big B, mu little c, mu big C. Now if we think about the different preparations of the identity, by preparation non-contextuality, they should all give us the same overall, mu over lambda. Let's call it nu. So nu is a distribution over lambdas which is equal to all of these. And the proof is quite easy now. Consider a specific ontic state lambda. Well, from this, we've got to have either that mu little a of lambda or mu big A of lambda is 0. And similarly here and here. So actually we've got just sort of 8 different cases to consider. Let's consider one of them. So for a particular lambda, suppose that mu little a of that lambda is 0, and mu little b of that lambda is 0, and mu little c of that lambda is 0. Well then looking at this line, we see that mu of that lambda is 0. And something similar happens for each of the 8 cases. So the conclusion you end up with actually is that this mu over lambda is 0 everywhere, which is a contradiction because this mu is supposed to be a probability distribution on a set of lambdas. So that establishes preparation contextuality for the qubit. Okay, and actually I think I'm going to yes, I'll finish with this. This won't make much sense to all the people who don't know what I'm talking about, but I wanted to put it in anyway, but I won't have time to do it all properly. But consider a system in a generalized probabilistic theory. So it's not necessarily quantum theory now. Such a system is simply associated with some state space which is a convex set. Now, measurement outcomes you can think of as maps from that convex set into probabilities. And suppose that the set of allowed measurements is the complete set with respect to the set of states. So by that I mean that for any map from the convex state space into probabilities, there is some measurement you can sort of physically do, such that one of its outcomes corresponds to that map. Well, then the system is contextual if and only if it is non-classical. So in this generalized setting, to say that a system is classical means that that convex set, which is a state space, is a simplex. Basically the system is just something with a finite number of different configurations, and its states are just a set of probability distributions over those configurations. So it's just a bit or a trit or whatever. If its state space is not a simplex, a probability simplex in that way, then it's non-classical. So an example is a qubit, because its state space is the block ball. And what one can show is that if it, for any system that's non-classical, given this assumption here, then that system is contextual. Meaning if you try and make an on-tip model for it, there's going to be either preparation or measurement contextuality in there somewhere. Okay, and I think for today we'll leave it there. Next time we're talking about psi ontology.